Last time we looked at how when charges move, they alter space, creating what's called a magnetic field, very similar to how a mass creates a gravitational field and a charge creates an electric field. Today, we're going to look at the force between magnetic fields. So, we showed last time that if you send current through a wire or just a charge that's moving, there's a magnetic field around that charge. And if there's a bunch of electrons orbiting the nucleus of atoms and all those atoms are aligned, it can create this overall magnetic field that will run from north to south. So if I have a magnet here and a magnet here, and the magnetic field's going from north to south here and from north to south here, the magnetic fields are opposing each other. They're going against each other, and that creates a force of repulsion. But if I have a magnet here, north and south, the magnetic field's going to go from north to south here, and from north all the way back to south here. The magnetic fields of each magnet are going to align, and that's going to create a force of attraction. So if I had this end of a coil attached to a positive power supply and this to the negative side of that, current is going to be going through this wire like this, and as current goes through there's a magnetic field around each charge. The magnetic field is described by that first right-hand rule we talked about yesterday. And the magnetic field around each part of these wires is going to combine to create this overall magnetic field. And then the convention is that magnetic field runs from north to south on the outside of this coil. In reality, these magnetic field lines are continuous. There is no beginning and no end. It doesn't start in one place and end at another place. It just is continuous. If you take iron and put on the inside of this coil, now iron has this special property that the atoms or the electrons that orbit the nucleus of an atom, their orbit can change through the influence of a magnetic field. So if this coil of wire has a magnetic field running around like this, the atoms that make up the iron can realign based on the magnetic field that it's in and create its own magnetic field. And what that's going to do is create a stronger magnetic field overall. So iron is used in the core of a coil to help create stronger magnetic fields. And then here, this is just a simple motor. I have wire that's wrapped round and round and round and round, an iron core, and I have that here and I have that here. One thing I should mention is that if you're going to make this, this wire looks like it's just bare copper wire. It looks like there's no insulation on it, but in reality there is this insulation on it. If this was just bare copper wire and this was current coming in and current going out, it would just go straight across the path of least resistance. But because it's insulated, the whole wire is coated in a non-conductive material, the current has to go through that wire, which is just going to be going round and round and round and round and round and round all the way through here. And then this is what's called a brush, and it touches this metal plate. Now this metal plate here is half of all the way around here, and the other metal plate covers the other half. This coil of wire here, one end of it is soldered, one end of that wire is soldered to this plate, the other end of that wire is soldered to this plate. So the current that's coming through here touches that plate, connects to that wire, goes round and round and round and round and round and round, back to that plate, through this wire here. That wire goes round and round and round and round, and then out back to your power supply. So basically, we have a north and a south magnet here, a north and a south magnet here, north and a south magnet here. the north end is going to try to align to the south end. And what I want to talk about now is what this piece of the motor is here. It's called a commutator. And it's an ingenious method of, just as this north end of the magnet gets to here, this brush, which was touching this plate, is now going to start to touch this plate, and vice versa. This brush, which was touching this one, is now going to touch this one, because the whole thing is rotated around. So just as it gets to be aligned, it's going to switch. We'll see that here. I'm going to move that around, and that brush here is going to cross over and now touch over here. Just the same moment, this brush now touches the lower plate. And what's going to happen is the current is going to go through this wire in the opposite direction now. So just as that north got to here, it's going to switch the direction of the current through that bar there, and it's going to switch the direction of the magnetic field. So here I have that commutator shown here. Right now, this brush is touching the upper plate and it's negative. This brush is touching the lower plate and it's positive. And that's what made the current go through this, making one side north and the other side south. And just as it makes half a turn here, when that one brushes over there and just switches from that side to this side, it's going to switch the direction of the current, and it's going to, again, make a repulsive force here and a repulsive force here. This is going to get attracted to here, and just as it gets there, it's going to cross over from there to there. And every time it turns a halfway around, the direction of the current through that coil changes, and it's always frustrating the effort of north to get to south. And it just, as fast as it can go, as fast as that motor can go, it just keeps pace and switches things. All right, so if I take a magnet that has atoms and electrons orbiting around, creating a magnetic field, and I put that inside of a coil like this, and then now I send current through that coil. The darker blue would be the magnetic field of the coil. The lighter blue is the magnetic field of our permanent magnet. And those two magnetic fields are going to try to align with each other. It's going to pull that magnet back in so that all the magnetic fields are aligned. And that's what I have here. A permanent magnet here, a coil of wire. Current is going to go out the positive, go round and round and round into the negative. And when I flip the power, it just pulls that magnet right in. The magnetic field of this is going to align with the magnetic field of that. And it pulled it in. And that's how speakers work. This is a coil of wire that is connected to either end here. And then right here is a permanent magnet. And when you turn the power on, so I'm turning it up, it's pushing that this way. And that would make the speaker push forward, making a compression. If I take those two things and I switch it now, I switch them like this. The current is going to be the other direction, so it's going to pull it in a little bit, and it pulls it in away from the air, making a rarefaction. If I connect it to the other side here to alternating current, current's going to be going back and forth here 60 times a second. The magnetic field is going to be changing 60 times a second, and it will just make that vibrate back and forth at 60 hertz. So how do you make music from this? Well, if you had 2 seconds worth of time here, so the first second, nothing is happening, and then you hit the drum, and then for the next second, it goes up and down, and just kind of dampens out. That might be what a drum would sound like. A sliding note like a trombone going from a low frequency up to a higher frequency might look like that. Playing one note for 1 second and then a different note for the next second might look like that. Loosely speaking, if we put all those together, you could call it music. And the music would just be the resultant of those different waves. So here comes the resultant of all those waves. And you don't have to play the individual waves, you just have to play the resultant of those waves. And instead of making this move forward and back, you have this be the voltage that is applied to that speaker. So a positive voltage would move the speaker up, and a negative voltage would move the speaker down. And just making voltage go that way would move the speaker in such a way that would reproduce that music. And just playing the voltage going up, down, up, down, up, down, up, down, going through all that through time would reproduce those sounds. And so this is the voltage going up and down. This isn't quite synced to it, but it's just making compressions and rarefactions in the exact same way that the resultant of many different sounds would produce. All right. Now we're moving gears a little bit. Instead of just saying we had a simple magnetic field in another simple magnetic field, what we're going to do is, let's say we have this horseshoe magnet. So there's these atoms in here, and all the atoms have their unpaired electron orbiting around here. That creates this overall magnetic field. And then over here we have the same. So there's going to be a magnetic field running from north to south here and from north to south here. So we have a magnetic field created from a permanent magnet. And then we're going to take a positive charge and we're going to shoot that through there. So this positive charge, because it is moving, that positive charge has a magnetic field around it. And because that moving charge has a magnetic field, the magnetic field of that moving charge, when that magnetic field hits this magnetic field, the two magnetic fields are going to produce a force. And that force is going to cause that charge to accelerate in the direction of the force. So I'll show you how to figure this out in a moment, but if the charge is moving this way and it hits a magnetic field that's going this way, it's going to experience a force down. And if when it hits this field over here that was going that way, well, it's the opposite direction of the field, so we might expect the force is also going to be in the opposite direction. So the charge is going to get pushed down here and pushed up here. And again, that's because when that charge moves, there's a magnetic field around it. And that magnetic field interacting with this magnetic field produces force. We have a second right-hand rule that's going to be able to predict the direction of that force. Now, maybe it's a good reminder to about the first right-hand rule we talked about. That's where we pointed our thumb in the direction of the current, the flow of positive charge, and then we curled our fingers around in the direction of the magnetic field. Okay, now we're not using that right-hand rule now. I'm teaching you a new one. So for this right-hand rule, again, we let the current, the flow of positive charge, be represented by our thumb. This time we hold our fingers straight, and those fingers are pointing in the direction of the magnetic field that charge is going through. So this would be like the magnetic field from a permanent magnet. And our magnetic field runs from north to south. So if we have a positive charge going this direction and it hits a magnetic field in this direction, the palm of our hand is going to point to the direction of the force that's created from the magnetic field of the moving charge hitting the magnetic field from a permanent magnet. All right, so just clarify our two right-hand rules. The right-hand rule where we keep our fingers straight is where a charge with a magnetic field around it hits another magnetic field. So this would be the moving charge, our thumb pointing that way. This is the magnetic field, that's this one here, and that goes from north to south. The palm of our hand would point to the direction of the force. This is the first right-hand rule we talked about, that when a charge moves, there's a magnetic field around it. So that's our magnetic field here. All right, let's see if we can predict. I've got a wire that I've connected. This side is positive, this side is negative. So we know current is going to be going through the wire like this, which means when we use our right-hand rule, our thumb should be pointing off in this direction to the bottom right. This is a permanent magnet. This side is north, this side is south. So our magnetic field from our permanent magnet runs from north to south. So if we take our right hand and point our thumb this way, point our 4 straight fingers that way, the palm of our hand would be facing down. So we know that when we flip this switch, the charges are going to experience a force down. And there it went. One more time, we turn it on and it pops down. We're going to cross these wires here now. So now the current is running this way through there. So our thumb is the direction of the current. Our thumb is pointed this way. Our 4 straight fingers still go from north to south. But when we put our hand in that orientation, the palm of our hand would be facing up. So the charges that go through there would experience a force up. Okay, now if I hook that up to alternating current, the current is going to be going back and forth 60 times a second. So for a moment, the force will be up, a moment it will be down, and it will just vibrate back and forth like that. And if you remember back to standing waves, we can see we have a node right there. All right, let's remind ourselves about circular motion. This is a swinging chair, people on here. These cables are being pulled inward. The chairs are moving that way. They're going in a circle around here. So if this is the direction of the motion, and this is the direction of the force, if those two are at right angles to each other, we call that a centripetal force. And it's going to move them into a circle. It's like if a car experiences a force in the same direction it's going, we call that positive acceleration. If the car is going that way, but it experiences a force this way, that's going to be negative acceleration. But if the car is going where the force is always at right angles to its motion, it would move that car into a circle. So if I took a positive charge and I hit that here, remember yesterday we talked about these X's represent a magnetic field going straight in to the screen. So our 4 fingers would be pointing straight into the screen. When the positive charge hits here, our thumb is pointing off to the right. Our palm of our hand is pointing up. So when it enters that magnetic field, it's going to experience a force up. But the force is always going to be at right angles to its motion, and that's going to move that into a circle. It's going to be, that force is going to be a centripetal force. All right, so if we did it this way, these dots represent a magnetic field that's coming straight at us. So if you can get your right hand with your 4 fingers pointing straight at you, the positive charge is moving to the right. So our thumb is pointing off to the right. The palm of our hand is going to be facing down. So when that hits this, it's going to experience a force down. But again, the force was always at right angles to its motion, so it moves it into a circle like that. All right, let's see if you can predict. Hit pause for a moment. Think about this. What direction is it going to go? All right, I hope you actually hit pause and tried it, but it will go down like that. And if we try this, I'm going to ask you to hit pause again for a moment and see what happens if a positive charge hit a magnetic field that was coming toward us. And it's going to go like that. And this is a technique that's used in particle accelerators, that if we take two particles and collide them into each other at fantastic speeds and they blow apart into all these individual particles, if a particle goes off in a straight line like this, and all that collision happened in a magnetic field, if it goes in a straight line, we know that that particle did not have a charge because it didn't have a magnetic field that would interact with that magnetic field. But if we see it circling this way, we can know if it had a positive or negative charge. If it circled that way, we could tell what the charge of those particles were. All right, now we're going to complicate things just a little bit, but let me remind you just of this, that if this charge is moving, it has a magnetic field around it. That magnetic field is going to interact with this magnetic field and create a force. And that's going to make that charge curve down like this. Okay? But the complicated thing is that motion is relative. So if I had a charge that is stationary, and instead of moving the charge this way, we took the magnetic field and moved it that way. Well, if this is stationary and the magnetic field is moving to the right past the charge, it's the exact same thing as if the charge was moving to the left through the magnetic field. So if that magnetic field moves to the right, it's going to push that charge down. And that's using your right hand rule, where your fingers are straight, to predict that. Okay, it's going to move that charge down like that. All right. Now, this is going to be an increasing magnetic field. This is where this magnetic field is getting stronger. And if the magnetic field gets stronger, well, it's kind of like taking a loop of wire and turning up the voltage. So more current is going through it. That would create a stronger magnetic field. A stronger magnetic field is going to have these field lines closer together. So if these field lines get closer together, here it goes. The field is getting stronger and stronger and stronger. We see that these field lines are moving that way past the charge. I'll do it again. So if we do that and it gets stronger, see the magnetic field is moving to the left past that charge, just like the charge is moving to the right through the field. So our right-hand rule would predict that it would get pushed up. And now we're going to decrease the magnetic field. We're going to take a coil of wire and turn down the voltage so less current is going through there. If the magnetic field gets weaker, these field lines are going to get farther apart from each other. See how the field lines are moving to the right past that charge? So it's like the charge is moving to the left through the field, and our right-hand rule would predict that the force would be down. All right, well, let's see how we can use that to make electricity, put a force on these charges and get them to move. If we had a coil of wire here and we had positive charges in here, I just have one blue and one red so you can keep track of which one's which. And we put that in a permanent magnet. So this would be the north end of that magnet. This would be the south end of that magnet. It would really have to be a horseshoe magnet where it continued back around. But there'd be a magnetic field going from north to south. And then what we do is we turn this thing around. We actually take a hand and crank this thing so this coil is turning around like that. Well, one problem is if you spin this thing around, these wires are going to get all twisted up. So to keep them from getting twisted up, we have these rings. So this wire is attached to this ring. This wire is attached to this ring. And then we have these brushes that slide on those rings, completing the circuit. So this red one, if this one gets pushed one direction, it will push this one that way. If this one gets pulled back, or if it gets pushed back that way, this one will get pushed back that way. So what we're going to do is we're going to crank that thing around. So at this moment, this charge is moving up and this charge is moving down. So if we take our right hand, we take our four fingers and point off to the south, because the magnetic field runs north to south. We take our thumb and point up, because that charge is moving up, we would find that that charge, our palm of our hand, would be pointing that way. So this charge would experience a force that way. This charge would experience a force that way. It's just going down through that magnetic field. Now, that's going to create the most amount of voltage is when it's going at right angles here. A moment later, it's now not going straight up, it's going at an angle through that field. So there only has a component up that's smaller. So you're not going to get as much voltage. So right now, this charge is moving parallel to the field. And when that charge moves parallel to the field, there isn't going to be any force on that charge, so no voltage. Now, this charge was moving up. Now it was moving parallel. Now it's going to start to head down through that field. So that charge that was pushed that way when it was over here is now going to get pushed this way because it's going down now, and we get a negative voltage. And now, because it's going straight down through the field, we get the most negative voltage. And now it's only going through at some component, so we get a little less voltage. Here it's going parallel. So when the charge goes parallel to the field, there's no voltage. And then here, and then here, and it just goes round and round and round. These charges get pushed back and forth through our light bulb, and that's how alternating current is made. And I think that is the end.